Hello there. I'm going to be presenting a tutorial on a gas dispersion, explosion, and fire type of simulation, showing everyone how to set that up with the CFD code. Now the code I'm going to be using is called C3D, which is available from c3dcfd.com if you don't have it, or you can use any CFD code that simulates combustion and fire. There will be similarities on how you set such a thing up. This still image that you see here is what we're going to be simulating. Let me describe it a little bit. What we have here is an oil platform with a pipe blowout that's dispersing natural gas, and it's being blown downwind towards a flare that's burning off waste gas. And when the natural gas reaches the flare, you're going to have an explosion followed by a fire. So let me rewind this little video and I'll play it for you. You can see the gas coming out of the blowout. It's being blown down towards the flare. And there you see the explosion and fire. And this is what we're going to be setting up. Okay, now this is ParaView, which I brought up the geometry. This is the oil platform. It's highly detailed. I don't recall the person that made it, but he did an excellent job. There's a huge amount of detail if you take a look. And all of that detail will be kept in the simulation that we're going to be doing. The original file that I downloaded off the web had far too many polygons to be used. So I had to use Blender to shrink the number of polygons, but even after shrinking, it still retained a lot of the detail as you see. So here's a little description of the setup. This is a flare boom, and this is flare gas that's burning. What they do out there, you get gas that is not very usable, and they just burn it off to get rid of it. And this is the drill platform. This is where the pipe blowout would occur on the inside. And there's going to be a source of gas from all these surfaces, which would represent the crude oil that has been blown out of the pipe blowout. So there'll be a couple of sources. We'll have a pipe blowout and crude oil, just surface sources. So the code that I'm going to be using is C3D. If you don't have it, you can get it downloaded off the web from c3dcfd.com, or you can use any other transient CFD type code. There'll be similarities on how you set up and run these codes. So the first thing you do is fire this up, and what we want to do is to actually it'll be a new project. We're going to be burning natural gas, so it's a combustion model, and we'll select methane. Okay. We'll go in and do some modifications. This is more or less the order that you're going to be setting things up in. They're already set up. A lot of this data has been set up for a natural gas fire. So one of the things that we want to do is to get some material properties. Actually, we don't need materials for this particular problem. What we need is gases. So let me cancel this. We already have an insulator type material, which is going to be used for constructing the floating platform. So initial fluids, we've already got air, we've got methane. Now we want to add us some flare gas. So right click, we'll call this flare gas. And we'll make it 50% CH, 50% methane. So 0.5, and we'll put in the rest of the mass fractions as 0. Most of these gases get created during the combustion process, but if you do have any of those in your initial mix, you can include those. So the pressure is going to be one atmosphere, 10 to the 5 pascals. Let's say 300 Kelvin. And so The setup that I showed in the video had a wind blowing in the y direction of 10 meters per second, so we'll put that in there. So it's 0 in the x and z directions and 10 meters in the y direction. Okay, so that will do the flare gas. We also want to modify any, actually we're going to use flare gas for the leak gas, so we won't change that. This will be the source gas. Well, maybe we should. Let's put in, say, 80% CH4, and the rest will just be inert gas, so I'll put in, say, 20% CO2. So that's going to be the gas that comes out of the pipe blowout. And air, well, let me show you what air is. We should put an initial velocity of 10 for the air as well. Basically the only thing that air consists of is oxygen, 0.233 mass fraction, and nitrogen. Okay, so these are the three gases we're going to use. Okay, I just realized that there is one thing that I do need to add to the initial fluids. And for this particular problem, if you just let it run with the gas sources, it takes quite a while for the flare gas, no, excuse me, the blowout gas to reach the flare for ignition. So what I want to do is create an extra bubble. So I'm going to add one more gas. So right click add, and I'm going to call this CH4 bubble. And what this is going to be is a large bubble of methane gas that exists at the beginning of the calculation. And the reason for doing that is so that you don't have to wait a long time for the CH4 to reach the ignition point. It basically just shortens the calculation so you can get it done in an hour rather than multiple hours waiting for the gas to get there. So let's put in CH4 will be 10%, 0.1. Most of these are 0, except oxygen will be 0.21, and the others will be 0. Okay, so that will give us a combustible mixture of methane and oxygen. Atmosphere pressure 1E5, temperature 300 Kelvin, and we want to give it an initial velocity of 10 meters per second. 0. Okay, so now we've got a CH4 bubble gas. So we have 4 gases. Okay, save that. Okay, so the next step is to set up the geometry, which is the floating platform. Actually, we'll go in and modify the size of the computational domain. The numbers you see are the defaults if you don't have anything set up. So it's going to be in the x dimension minus 100 to 100. The platform is actually quite large. It's about 100 meters squared, but we're going to go up beyond that. And the y directions go from minus 100 to, say, 150. And the z dimension will go from the sea level of 0 and up to 200 meters high. And the whole thing will consist of air. So that'll be the computational domain. Okay, the next thing we want to add, right click, click on add, is a STL file, which will be the floating platform. And it's going to be an STL graphics file. It's going to be called STL, no, Oil Rig 4, I forgot the name of it. Rig 4, now I remember, RIG4.STL. And You can put in a fluid. It probably won't include any fluid, but you can. It doesn't hurt if you do that. The only material that we have is insulator. We could have made it from some other smaller material if we included that. So the parameters that you see here are how to take your STL file and shift it in space and how to scale it. So I just took a look at the STL file. So the X and Y shift are both 0, and the way it was set up, it had to be lifted by 61, whoops, yeah, 61 meters. And the scale factor will be 1. The original file, I believe, was in millimeters or some strange units, and I had to rebuild it to get it to be of an appropriate size that I could use it. The last thing here is solid fill, reverse fill, or thin shell. What you want to pick is thin shell. A solid fill or a reverse fill is okay if you have a simple geometry, then it knows what's outside and inside. But if you have a complex geometry like this floating platform is, it doesn't really know what's outside and what's inside. So what a thin shell will just fill in the actual STL with solid. So you can have regions that are basically empty boxes and so on. So, okay, that pretty much does it for the STL file. We'll click on OK. We're done with the geometry. Okay, so I have to bring the menu back up. Here it is. The next thing we want to do is set up boundaries. What we're going to do right now, the default is, let me show you what they are. It's basically air on all the boundaries, and that's just fine. And it also has a 0 flow boundary on all the boundaries. And that's okay. What we're going to do is we're going to modify it. Now, actually, let's go in and modify this one to be hydrostatic pressure everywhere. And we have to give it a temperature in case there's inflow. It doesn't really know what the temperature on the boundary is at this point. So we have hydrostatic pressure. Now, the other thing we want to include is a wind on the Y-min boundary. So that'll be mass flux and temperature on the Y-min boundary. And that was a 10 meter per second, or kilograms per meter square per second. Turns out the density of air in SI units is about 1, so that's why I'm using mass flux and velocity interchangeably. So 300 for the, whoops, let me click on that one, 300 for the temperature in Kelvin. Okay, so now what we have is a hydrostatic pressure everywhere. On the Y-min boundary, we have a inflow of 10 meters per second. And on the bottom, we want to have a no-flow condition. So Z-min, right here, adiabatic no flow. Okay, so that does it for the boundary conditions. Okay, so the next thing we want to do is mesh the geometry. We'll go in, and these are the axes. You want to do all three independently. So the simplest way to do it is to be right-click, do a delete scan mesh, and what this does is it scans the geometry to see what you've got and sets up a mesh. We want to do 100 cells in the X direction. So it goes from -100 to 100. That was the domain that we set up, 100 cells. And they're 2 meter on average. The Y, we want to do a delete scan mesh here too. Remember, this goes to 150 meters. So we'll do, let's put in 120. Yeah, 125. And what we want to do is, well, you can't edit this line, but you can edit this one. We want this to go from minus 100 to 100. See, it put it here. So that'll be 100 cells in this section. And for the remainder, we want to have a stretched grid of 25 cells. And we want to stretch it with a power law, growing in the positive direction. So that'll give us the 125 cells in the Y direction, which is the direction the wind is blowing. And for the Z direction, right-click, delete scan mesh, and we want to add 100 cells. Okay, and they'll be uniformly spaced 100 cells, so up to 200 meters. And that's all we want to do for the mesh. So one thing I forgot to do in the geometry was to set up the initial gas bubble that's going to be advected downstream to the ignition source. So I'll go back into geometry, and I think you can drag these things around. We'll give it a try. All right, let's call this, well, CH4 gas bubble. And it's going to be a spherical region centered at XY0, and the platform floor is at 50 meters. So we're going to center that sphere at 50 meters, and the radius will be 40 meters. And it will consist of CH4 bubble gas, and that'll be it. Okay, now one thing we want to do is we want to move this spherical region ahead of the STL graphics file, because if we put it after, what it's going to do is erase everything within the sphere, and then there won't be any geometry inside. So I think what you do is you press the control button and drag it up. Yes, it did that. Okay, good. I'm glad it worked that way. Okay, and then we'll save that. So the next thing we want to do is to set up the 1D subgrids. Right, there are none by default. The subgrids are going to be used for setting up the flare and also for setting up the pipe blowout. The flare is going to be a line source. Let me show you how I set that up first, and then we'll move on to the blowout source. So right click, we want to add a subgrid, and we'll call this flare. We'll call this flare. You could have multiple parts, but we've only got one. Flare, length of 1, and we're going to use just one cell. So if you use one cell, what flows into that cell flows out. So it's whatever gases you have, and that's flare gas. And it's going to use the composition, temperature, and all that. Boundary conditions here. On the min boundary, I think you double click here. Yeah, double click. And on the X min boundary, it's going to be, we'll call it momentum, and it'll be the 3D pressure because it's going from the subgrid into the 3D domain. That's why you use this boundary condition. On the right, we're going to give it because it's going in the negative direction, we're going to give it a negative flow rate. We're going to give it 1 kilogram per meter squared per second at, we'll give it a temperature of 300. Actually, it's going to be hotter. Let's make it 800. Now, we don't really know how much flare gas there is, and that's going to be set up as a line source. So we got pressure, mass flux. The next thing we want to do is use a line source for that. And I'll show you how to set that up in just a moment. But we have to give it a name. We'll call it flare.inp. INP stands for input file. Okay. We'll do that. And I'm going to show you how to set up that file next. I think that pretty much does it. So I just realized I made a mistake on this flare subgrid, and that is the direction of flow. I set it as 1, and it needs to be -1 because it's flowing from the x-max boundary to the x-min boundary, which is in the negative x direction. And that will cause it to flow out of the subgrid into the 3D domain. Okay, so we're done with this. Now, in order to set up the line source, we need to know where it is. And the best way to do that is to open up ParaView. So I'll leave that open. We'll go into run. Oh, got to save the data first. So we'll go to our desktop. And it's in oil rig tutorial. And we're going to call it C3D-INP. Okay. I want to open ParaView. Okay, so I've got ParaView open. What I want to do is open a file that has the thing. Now I've run this before, so I do have a file C3D-VTK, and you will eventually create those when you run it. I'm just going to open the one I have. Okay, here is an image of the platform. I'll zoom in, and this is the flare boom here. Let me change it to be solid color. So what we want to do is to create a line source on this at this location. So simplest way to do that is to click on ruler, click on the location you want it, and hit the P key. And it comes up with the X, Y, and Z coordinates right here. So we copy those down and then go back and create a line source from those coordinates. So now that we have the coordinates of the line source, what we need to do is to create a file called flare.inp. So I'm going to open a text editor with a new file called flare.inp. Now the format of this file is quite simple. The first thing that you input is the number of line sources, and you can have any number you want. It could be 500,000, whatever you want, but in this case we're going to use 1. So the data that goes in there are the X, Y, and Z positions, and the X coasts, Y coasts, and Z coasts directions, the area of the subgrid in meters squared, and the length of the subgrid. So from ParaView we got these coordinates, -0.6, a Y of 77, and a Z of 86. The X coast is 0 because it's aligned with or it's parallel to the Y-axis. And we're going to use a Y-coast and a Z-coast of 1. These do not have to be normalized to 1. The code will do that for you. So I'm just going to put it 1, and that will give a 45-degree line source in the YZ plane. See, area of 0.5 meters and a length of, say, 4 meters. So that does it for the flare.inp file. We'll save that and move on. So the next thing we want to set up is the pipe break. Let's see, let's close this, and we'll go in. We want to add a second subgrid, and we're going to call it pipe break. Again, let's just call it pipe here. The length will be 1, and we're going to use 1 cell again. The fluid will be methane. The X-min boundary, it'll be the same thing. Double click. It's going to be, we want momentum and 3D pressure. So it's going to flow from the subgrid into the 3D domain. And for this, let's see, there's several different options on how we do this. We could have it as a surface source coming off of the materials, which would simulate evaporation. I think we want to do that because we're going to follow this with a fire. So we'll double click here. What we're going to have is a combined mass flux and temperature, and we're going to give it a mass flux of minus 0.06, and that's typical of a pool fire, 450 Kelvin. A pool fire, so that when after the explosion, what we're going to have is a fire, and it'll be coming off of a bunch of surfaces with this kind of a mass flux. Okay, and it's methane, pipe break. It's all set up. And what we want to do here is couple this to the geometry. And the only geometry we have is the STL file. For now, let's pick the entire domain. We need to modify that so that it doesn't come off of anywhere. We want to restrict it to a spherical region. Well, actually, let's do it this way. Let's go from a minus 30 to 30, in the y direction, minus 30 to 30, and the z direction, let's go from 30 to 80. And that'll create a box that contains the line source. But what I actually prefer to do would be to create a sphere, but let's leave it as a box for the moment. We'll save the data because it's already, here we go, it's saved. Actually, let's run it for one time step, and we'll see what we've got. The default is to run it for a single time step. Okay, so we're going to run the code, and if there's any errors, they'll show up here. So here's the coordinates that were found in the STL file. Let's see, it says one input error, and here's the error. It's in the subgrid mapping. Volume fraction of gas is 0. So this is the it looks like it's the flare. So I got to go in. I know that because the face area is 0.5. I got to go in, and what's happened is that I didn't actually shift the line source to be away from the end of the flare, so it's putting it in the flare. I got to go back and edit the file. So let's edit the flare.imp file. And what we've got are these coordinates. The flare is actually inside, so let's move it out 2 meters in both the y and the z, so 88 meters. Let's move it 3 meters just to be sure it's beyond the end of that flare stack. So we'll save that and then go in and run it again, and hopefully it'll run this time. Okay, problem completed with 0 time step. So it ran successfully. Let's take a look at the mesh. Okay, it's pretty large. There's the mesh that we have set up. So for C3D VTK, let's turn off surface with edges, just a surface. And there you can see it's a fairly fine mesh, 100 by 125 by 100. So everything's set up successfully. Now the next step is to actually put in the source for the pipe break. Actually, I think we set that up. So the problem we're going to run into is that the pipe break is actually fairly small. I mean, a fairly low mass source because it's just coming off at a evaporation rate that you'd find in a pool fire. So what we want to do is add another line source. Let's go ahead and add one more. Add a pipe rate, and we'll call this the blowout. And it too will be a line source. 1, 1, 1. And let's make that, let's make it methane. And it's going to be a line source. We'll call it blowout.inp. That's going to be the name of the file. Xmin will be the same as before. It'll be a momentum 3D pressure boundary condition. And the right, now it's going to be choked flow coming out of this pipe. So mass flux and temperature, let's give it a velocity of say 200 meters per second and a temperature of 300 Kelvin. Okay. The CH4, let's see, and a pipe look. All right, now so that sets up the blowout.inp. Now we need to edit a file called blowout.inp. So I'll create a file called blowout.inp. Actually, let me copy flare.inp. We'll just modify that. Copy flare.inp to blowout.inp. And then we'll edit the blowout.inp file, change its coordinates and so on. So now the center of that flare is 0, 0, 0. So I'm going to put in 0 and a y of 0. And the platform floor level is around 50 meters. It's going to blow straight up. So x and y cosine are z. So let's give it an area. Now it's choke flow. The pipe diameter is going to be small, but that's going to end up with a pretty high velocity. Let's give it an area of, well, 0.5 meters is fine. And a length of, say, 10 meters. Okay, so we've got a pretty big blowout, pipe blowout. So that's what we're going to use here. So I think this is pretty much ready to go. So what we need to do is save data. Okay, now we're going to go in and make sure it runs. Same as before. Hopefully we don't have any errors of any kind. We'll know in just a moment. Okay, it ran. Problem completed. So it ran successfully. Let's close this and make it go for, whoops. We want to change the time. Print every time step. Let's go for 10 time steps just to be sure it goes. Restart options. We want to write a restart. Let's see, we may run it more than once, so we'll do a skip subgrid. So if we do a restart, it'll always use the subgrids at the beginning condition. Stop time, let's make this 30 seconds. It won't run very far in time because we got a max number of time steps of 10. But all we're doing now is testing it to see if it's going to go. Okay, I do see one problem. Up here it says we're running with a single processor. We want to increase that to, I don't know, we'll go, this isn't a very big machine that I'm running on. We'll go with, say, 6 processors. It looks like it's running okay, so I'll go ahead and stop it. Okay, so let me close this. We got to make a couple of changes now. We'll go into numerical parameters, and we want to increase the number of processors to, let's go with 6. I think that'll run on this machine. The other thing we want to do is ignite the flare. So CH4 has a fluid temperature of 300. We're going to change that to 800. Oh, no, cancel that. CH4, make sure, yeah, 300 is fine. The flare gas is what we want to be hot because that's going to be our source of ignition. So we'll make that 800. Okay, it's going to be injected into the 3D domain at 800 degrees. Now, we have to go into chemical reactions and modify all of those. So we've got all these chemical reactions. The important one here is the methane reaction. We want to set that min reaction temperature to be, let's say, 400. Now, everything in the system right now is cold, but when the methane heats up to 400, it's going to ignite, and that's how we're going to ignite the flare. None of these other gases will even be in the system, so we don't really need to worry about those. Let's save data. Okay, and now we'll go ahead and run it. Let's modify and run it till, let's make this 1,000. And when we see the temperature getting hot, we're going to stop it with a restart. Okay, so now we're going to let it run. And hopefully everything will go just fine. I'll put this on pause while it's running. So it's been running for a while. I actually stopped it earlier. What I'm going to do is kill it. I found that the flare that was set up was not burning, so I got to go in and fix those errors. So go back to 1D subgrids. Another thing I noticed that the blowout, I had a positive velocity. That's at the X max boundary. It needs to be a negative velocity. It's actually increase it a little bit. A negative 250 kilograms per meter squared per second. Okay, and the other one was the flare. This was set at -1. A -10 would be more appropriate. That would give you a sizable flare. And it should heat up now enough to cause ignition of the flare. And that's what I was looking for. Save it. Okay, I'm going to run it again. And I'll put the recorder on pause while I watch it run. So the code's been running for about, I don't know, 0.8 seconds now. We want to see how hot the flare gas has gotten. Bring up xplot, xcenter. That plane runs right through the center of the flare. If we take a look, go to the last time step, and it looks like it's gotten to about 330, 340 degrees. So we could ignite the flare by lowering the reaction temperature to that region. I think we'll do that, and that way we can go ahead and run the calculation out in time. So we're going to stop with a restart. Close this. It's been running with a 5 millisecond time step. That was the default. I'm going to increase that so it. First, let's do the restart options. We want to, reset time to 0. We want to both read and write a restart, and skipping subgrids is okay. It's just going to set them up at their initial condition. The max, well, let's make this 10,000 for the max number of time steps. And DT max, let's make that 10 milliseconds. 0.01. Okay. Now we go into chemical reactions. We're going to lower the methane reaction temperature to be just below what the flare temperature was, and that was about 330. We'll make it 330. Whoa, not 300, 330. And we'll see how that runs. Okay, save data, okay. Now it should ignite. We'll run it and see if we get ignition. Now all we're trying to ignite at this point is the flare. And if the flare lights, it'll get very hot, and we can save that as a restart and reset the gas ignition temperature again. There we go. Yeah, it lit. You can see reaction temperature 721 megawatts. So that's a lot of gas that just burned up almost instantly. So now we want to stop this. Let it run for 3 seconds. Stop it with a restart. It looks like it runs with a 10 millisecond time step, so we're going to increase that to 20. Oh, let's go all the way to 30. 30 is a good frame rate for videos. So we'll go back to here. We'll make this 30.03. Now, it is already lit, so we can change this back to the auto ignition temperature for natural gas. That's about 600 Kelvin. I'll make it 500. Okay, save data. Okay, now we go ahead and let it run, and we should end up with a result similar to what we saw in the video. We'll let this run. I'll put this recording device on pause and come back after it's run for quite a while. Okay, so the code is run out to 30 seconds. That took 2 to 3 hours, something of that order. I'm going to show you what's going on. I can tell by the heat generation rate, 1600 megawatt, that it's starting to ignite. Let me run xplot. Bring it out front, and we'll look at the reaction energy, and you can see this is just the flare burning at this stage, and at this point we're starting to get some methane from the pipe break, and here it's starting to take off. So when I restart the problem, it'll probably continue to go through its entire ignition sequence. So it needs to be extended, and the way to do that is to restart it. We'll go in, and we'll let it run to, say, let's go to 50 seconds. And restart options. We don't want to reset it to 0. We'll skip the subgrids. Read and write, restart, all that looks okay. One thing I did notice is that the VTK files, the output time is 1/10 of a second, not 30 milliseconds like I thought. Oh, there is one thing. We want to continue this from a restart. We do not want to start at 0 again. That way we have a continuous sequence of files that we can use to create a video. So I think this is ready. But one thing I want to do is to save the restart in case something goes wrong. So I'll copy restart.inp to restart.backup. I'm only doing that in case something goes wrong, that I'll be able to redo it. Okay, so now we'll continue the run. Oh, actually, rather than doing that, let's look at ParaView. Okay, this is ParaView. I'm going to open a state file that I created earlier. Whoops, not save it. I want to open it. It's a PVSM file that saves basically all the data that you had set up previously. Okay, so this is looks like VTK file 211. At the current time, we have, I think, about 300 of these VTK files. So you could see the methane gas it's forming here. There's kind of a wake behind the tower, so that's why it's taking so long to ignite it. And you can see the flare burning here. So everything looks normal. And let me reload the files and go to the point where it's just starting to ignite the flare. We'll go to the last frame. There it is. Okay, so you can see that the gas is finally gotten. Well, it doesn't show up. I probably need to do a maybe 0.02. Whoops, wrong one. This is the methane one, CH4, yeah, 0.02. Okay, here you can see that the methane is finally starting to reach the flare. I think we'll save this as a new state file. Bring it back to 1. And we'll save that. Okay, so we don't need ParaView anymore. We're going to let this problem run. See, the setup has already been done, so I think all I got to do is run it. And then we can make a video of the explosion. Okay, so the first time I ran the code, I was getting ignition starting at 30 seconds, and that was taking too long. So I actually went back and I added that spherical bubble and re-edited the file. So just as a reminder, I added this spherical region. So, and that allows the ignition to occur much quicker, actually in about 10 seconds. So let me cancel that. I'm going to bring up ParaView to show what the ignition looks like, or what the initial setup. This is the flare that we got burning, and this is the very first time step from the restart. That's the spherical region. It's deformed a slight bit from the original spherical shape because I think it ran for 1 or 2 seconds just to get the flare lit. But you can see the blue region is the real large gas bubble. And again, the reason for including this large gas bubble so that when the wind blows the gas bubble down towards the flare, it'll ignite much quicker than it would have taken otherwise. So I reran the problem with this spherical bubble in there, and I'll show you the result. Okay, so here it is at time 0. The flare is lit, and recall that we're running this from a restart. So you start getting ignition right around, I changed the output frequency to be 30 milliseconds so that it's more like real life rather than accelerated time. So around frame 260, you start getting ignition. Now it looks like the gas has gotten there, but it really hasn't. And the way I can show that is to bring up the gas opacity to 1. So you can see that the flare is nestled inside a wake zone created by this tower. However, it won't take long before the ignition actually starts. Let's go up to frame 280 and take a look at that. Okay, so you can see that the ignition is already, it's progressing. So I'll continue to let this run so that we get the fire after the ignition, and then we'll make a video. Okay, so the code is finished running, and with the bubble, the ignition occurs a lot earlier in time. Let me show that with XPlot. It always jumps to the back. I got to bring it to the front. So if we look at global history and down to reaction energy, you see that there's basically all there was the flare, and this is the total energy generated within the domain. And you can see right at about 8 seconds, there's a huge pulse. That's the explosion, followed by the fire, and the fire is generating. It's hard to read the scale, but I don't know, a few hundred megawatts. So let me show the video that was created. Go back to here's the video that I made from a side view, and you can see the wind is blowing the big gas bubble towards the flare. And when it reaches it, you'll have this sizable explosion. There it goes. And then after the explosion, there's a fire. And a couple of interesting effects. The fire basically, the wind is still blowing, but it kind of stops it. The flare is in the wake zone. It's also very tall due to the lack of oxygen at this point. Most of the oxygen got burned up in the explosion. And this will reduce back to its original size. And the flare will keep burning because we gave it a fuel source. Here it is the second time. I'll show this one more time, and then I'll show another video I made of the same thing, but actually I added rotation to it. So that's that. Now let me show this other. This is basically the same video with rotation added, so you can see more of the domain and the platform. There it explodes. Fire's burning. So in summary, I'd like to point out that in this tutorial we have an oil platform, and it has heat sources, a blowout gas, and a gas source. And there is a ignition source, which is the flare burning off ordinary gases or waste gases. And you get an explosion when the gas hits the flare. The wind blew the natural gas to the flare, and you get ignition. And then after the ignition, you get a fire. So hopefully this explains how you can set up this kind of a video. And of course, there's a lot of parameters that you can change to make this even more realistic. But I'll leave that up to the viewer. And that's all I have for now.